So practically speaking, for any given masking system, there's a cost process time benefit of being able to use the minimum top layer resist thickness to obtain the desired result. Also for, LOR and PMGI materials, they're basically recognized for much higher temperature stability than most imaging top layer resists. Typically, they can go up into the range of 200 degrees C. So Kayaku Advanced Materials, we looked at this as a problem where we thought we could expand the capabilities of the bilayer if we were able to raise the top layer resist temperature. And as you can see, we did stress tests on these structures, and they were stable up to and exceeding 170 degrees C. So for reactive chemistry depositions like nitride or oxide depositions by low temperature PECVD, this may open up some potential windows for use of masking structures that may not have been accessible before. Some single layer resist systems, they just seem to not work quite as well at accelerated temperatures, like the 150 degrees C deposition here of nitride. You can see how that material shifted in its stability prior to and then after deposit of the material. And in comparing that to the images shown above, with both basically a 2.3 micron top layer of high temperature resist and a 1.5 micron layer, both show very good stability for depositing a similar type of material. Likewise, we looked at basically the performance of the top layer resist changing to the high temperature version and compared that to the lower temperature SPR resist that the model had suggested. And we found that there was still continued good correlation, suggesting that this RD ratio undercut is largely influenced by the deposition type as well as the material. So basically, the model shows good performance to 5 micron lines and spacing capability. It offers unique geometry adjustability, and overall works well with conformal processes or reactive type chemistries.